right, prove triangle properties. Segment AD is an altitude of BC. This is not to scale. Which of the following additional statements would allow us to prove that AB is congruent to AC? Okay, so we know that it's an altitude, which means that's a right angle, which means that's a right angle. So we know those angles are equal to each other. We know this side is equal to itself. So what we really want is this to be equal to this, that it cuts it in half, that it bisects it. Another angle also would help if we had another angle, because then we could do, if we did the side, we'd do side, angle, side. If we did an angle, we could do angle, angle, side. So there's a couple of different things that would help. CD is congruent to BD. That would definitely help. CD being congruent to BD would give us exactly what I said just a second ago, side, angle, side. Angle B is congruent to angle C. Well, that also would work. Now, I don't think you need both statements, but either statement is sufficient. If you got one or the other, that would give us all we need. And this congruency stuff and proof stuff is probably some of the hardest stuff we got. So don't get too freaked out by it. We won't be doing it for a horribly long time. It won't be something that'll pop back up as much as many other things. Some of the definitions will, but not so much other things. Okay, so AB, complete the proof that we're given. AB is congruent to BC. Construct BT as an angle bisector of ABC. So you're going to have some line coming right down the middle. All right. So definition of angle bisector means it cuts an angle in half. So ABD and CBD would be the same angle. Then triangle DAB and DCB are congruent by which thing? Well, what did we talk about? We talked about a side, and an angle. We did a side, and the angle in between. Side, angle, side. Now, I know it's not drawn in here, but you can visualize it. So this is side, angle, side. Did we prove the conclusion for every triangle or just the specific? There is no specific numbers here. It's not like we said this is 3 and this is 3. So this is done with a generic proof. This is for every isosceles triangle. The only way it wouldn't be for every isosceles triangle is if we gave specific like angle measures or side lengths. All right, try to prove that MN is congruent to MP. Okay, let's see how she did it. She said, okay, these two angles are congruent by definition. She constructed a perpendicular here. She said those two angles are equal, okay. Then she said this triangle is congruent to this triangle by angle, angle, side. What are we given here? Okay, so we got that. That's equal to itself. Angle, and then that's a right angle, so that would be angle, angle, side. Yep, I actually like that. Angle, angle, side. Corresponding sides of congruent figures have equal lengths. Okay, what was the first mistake? Maybe what's she saying in MN and MP? MQ. So then MQN is equal to MQP, which means you've got that angle, that angle, that angle, that. Oh, she left something out. She didn't say the thing about MQ equaling itself. So she left a phase. She had everything set up. She just didn't say, hey, MQ equals itself. That's all she missed. That's why it was hard to see, because she did everything correct. She just forgot to say something. All right, which of the following additional statements would allow us to prove the sum of the interior angles is 180? Okay, point C is on line L. The figure is not to scale. Okay, we need that this is parallel. If this is parallel, then 1 equals 4, 2 equals 5, And 3, 4, 5 add up to 180, so you substitute 1, 2, 3 have to equal 180. Again, guys, I know this is one of the hard ones. We'll suffer through it. We'll be okay.